I'm Yoav from Bar Ilan. Initially, my talk was called Doing Stuff with LSTMs because we do stuff with LSTMs. But then I decided that like everyone is doing stuff with LSTMs, so let's see. And they all say that they work, so now let's see where they fail. But I will start with a few words about myself. So my research is about the core building blocks for NLP. Using machine learning. So basically, it means that doing stuff with LSTM is doing NLP with machine learning. And I have a book on this topic. And we have been doing a lot of stuff with LSTMs because LSTMs are actually very good learners for sequential data. So one of the things that we definitely do is just use them to build stuff. Is there a timer? So use them to build stuff, and we try to do it in an interesting way. So to kind of have some edge in how we build things. And then we have plenty of works in this area. So we had a nice work on chunking, tagging, and compression with multitask learning. This is from colleagues from Copenhagen. We had work on parsing, which is basically taking a sentence like this and then producing its structure. We had for some period of time the best parser in the world. Now Stanford won, but we are trying to get back on top. Yeah. And then we also had this work with Vered and Ido, where we basically read a lot of text and we try to learn facts such as that Tuvalu is a country, Ninja is a weapon, and so on, by just reading Wikipedia. Of course, people have done this before, but we improved the results by a lot using LSTMs. This work about coordination, I will skip, but it's a cool work. Inflections, so how to inflect words. This is with Ro'i. Here, we worked on fine-grained senses for prepositions. So the word for can mean different things. And we try to kind of decide what it means in context. The problem here is that there isn't that much data available for training. So we did multi setup where we improved using monolingual data. This is with Hila Gonen. Ro'i again did translation and improved the quality by using parse trees. So just by changing the output of the network, we can get better results. And this stuff is also pretty cool. We were doing generation, but we're trying to control what is being generated. So for example, here you want to generate a sentence about movie review, because that's what everyone cares about these days. And you have this table of values. I want to generate something about the plot of the movie with which is in favor of the movie. It's written by an audience and not like a critic. And it should not be subjective, so no I or my, with some length and with a few adjectives. And then we generate things like that, which, okay, they're pretty good, I think. And then we can change the values, and we ask for some other theme, negative sentiment, audience. This one is subjective, so I have I or my in the text, and many adjectives. And then you get things like the one on the bottom. Ultimately, I can honestly say that this movie is full of stupid, and stupid, which actually fulfills all of the requirements, which is quite nice. And it actually does it in a creative way, I would say. And people do work like that. So this is kind of a success, I think. Okay, so we use them to build stuff. We get strong results. Reviewers are very happy. We publish many papers. Many architectures, that's nice. There is a big team here and with so many good collaborators. And then we also build tools to build more stuff. So this is DyNet, our library for neural nets. It's developed mainly by Graham Newby at CMU, also Chris Dyer at DeepMind, who initiated this great project, Paul Michel at CMU, and myself. And this is basically a toolkit which is geared towards NLP stuff with dynamic neural networks, pretty much like PyTorch, but better in many ways. So if you're doing vision, use PyTorch. If you're doing NLP, try Dynet. It will save you some time. I think we are both more efficient currently than PyTorch, and we have some nice features that actually save time, like this auto batching, which I will not describe today. But it's cool, try it out. And then the other thing that we can do is to try to understand how they work. And this is also a very interesting line of work. I think it's the most important one, almost. And we do have some works about that. But in this talk, I would like to talk about exploring their limitations. Okay, so cases where they don't actually work so well. So the actual title of this talk is When Deep Nets Fails, and I just kind of give you an overview of some cases where we either tried to use them and they failed, or we show that they fail. And this is not only for RNNs, and not only for NLP. And I will start with the SNLI task, the natural language inference, which is basically a kind of the previous name was textual entailment. So there is this data from Stanford. You have pairs of sentences, okay, and you have to decide if the first sentence entails the other. Like if the first is true, does it mean that the second is true as well? So a soccer game with multiple male playing, some men are playing sport, it's entailing. And at the top, you can see a man inspect the uniform of a figure in some East Asian country, and the man is sleeping is a contradiction. Okay, so and you have to train a network or come up with some other way to give in a pair saying if it's neutral, contradicting, or entailing. And Stanford created this huge data set over 500,000 of human-written pairs, each of them with human labels. And there is a leaderboard of many different systems. These are the best ones. They do 89% accuracy on this, so it's pretty impressive. And in this work with Vered and Max, what we try to do is to say, did it actually learn what it is supposed to, or does it have blind spots? So we did this very simple experiment. We took a sentence from the train set, so it's known to the network. And then we change it with a single word. So here we change the word yellow to red. And now this pair is contradicting because it cannot be both yellow and red at the same time. We also did this here. So the man is wearing a yellow shirt and playing a piano. The man is wearing a yellow shirt and playing French horn. Okay. Chinese flag, Vietnamese flag. Okay, so again, similar case, but some fact which is different. And we have like 10,000 of these or so. And these are very, very easy for people. I mean, they're trivial, basically. But when you feed them to the networks, you see that they drop from 86 to 89 to 52 to 65%. So it gets most of them wrong, which for me kind of means that these networks are not really learning, or they did not really learn the inference task, because they fail on very, very simple cases. And now, this also kind of raises some questions, like how many training examples do we actually need to get this right, right? We have like 500,000. Maybe we need more, but maybe this is really not the most effective way of doing this, right? Maybe we can inject this knowledge in some more structured way and not rely on an end-to-end approach. Okay, so that was the first federal case. Now let's move on to this case. So this is with Roy, and we worked on this task, which is called split and rephrase. So here the task is to have this sentence, which is long and complex, and we want to translate it or like split it into 3 sentences, which are each simpler and express all of the facts in the main one. And there is also data for that, so we trained the model, and our Roy's model, the neural seq-to-seq with attention and some improvement, got really good scores on this data set, about 80% blue, which is way above all of the other systems on this data. But when you actually look at the results, what you see is that for a sentence like that, a fortress of gray ice, ISBN, whatever, has pages, you get that, okay, it got the fact that it has 672 pages, but it also got this fact, which is J.V. Jones authored this book, which is true, but not in the sentence. And it also got the fact that this is a fantasy novel, again, a true fact, but not in this sentence. So it appears that the network did not really learn to simplify, it learned to spit out facts about some entity that it managed to find. And you actually get good BLEU scores from that. And then we can also try like adversarial examples. So you just tell it Alan Shepard, and it tells you that he is dead and he was a test pilot, okay? Which is, yeah, nice. And if you look at the attention matrix, it actually kind of makes sense now. You see that the attention is all over the very, like one word, which is the kind of main entity, and then it just try to make up facts about it. Now, having a network or a model that will give you facts about an entity is nice, but this is not what we wanted to do. And it's also, there are easier ways to have this behavior, right? And the lesson here is to basically not trust BLEU scores, to look at the outputs, and also be very careful when you design test sets, because if you can get very high accuracy by cheating in this way, it means that there is something flawed in this data. And since then, we improved the data and we have a much better split, and we also have a better model, but this is not the story here. And still, I mean, this thing actually fail quite a bit. Okay, so this one, so here this is a very nice work where we tried to extract automata from a trained RNN. And it's a nice technical work with Gail and Yoav from the Technion. Basically what we say here, and that's not a failure, that actually works, we're saying, okay, so there is an LSTM, and we have a state vector, and some input symbol, and then we have some new state, and then we have some decision for like accept or reject. And this is very similar to a state machine, okay? But these states are like continuous vectors. And what we try to do is to extract like an FSA or an automata from a trained RNN if it's simple enough. Okay, and that's hard to do, but we managed to do it. And then we trained an LSTM on a language like that, of like simplified JSON lists. And then we extracted the perfect FSA for it, and it worked very, very well. So we can actually extract an FSA from the network. But then we tried it on some other language. So this is balanced parentheses up to a depth of 8. Okay, so it's basically A to Z and parentheses, and it's like random letters, and it has to be balanced. Okay, and we trained an LSTM of that, and then we kind of did the extraction, and it works in stages, and it kind of gets you more and more elaborate FSAs. And this is the kind of last one, the final one, and you can see that it's kind of accurate. But it's not like a nice chain like you would expect. And if you look over here, you see that it is actually not quite right what's going on there. And there are definitely many cases that it will accept where it shouldn't. So even though it's trained to perfect accuracy on the train set, and it's a very simple language, you see that it's actually learned a very different function than what we wanted it to learn. Same for emails. We have this very simple expression that will define what a valid email is. Okay, so there is definitely a very simple FSA for this expression, and we train now on 20,000 positive and 20,000 negative examples, and 2,000 examples in the dev set. It trained to perfect accuracy on both of them. And then, when we try to get out the actual FSA, we see that the algorithm did not converge and we kind of stopped it when it got to 500 states, which is way too many. So it learned a very, very, very complex function for this data. And this function actually accepts these, which are not valid emails, and they don't have the kind of @ sign. So basically, the LSTM that trained perfectly and had perfect accuracy with a very simple function did not learn the right thing. Okay, so you should be afraid of what your LSTM or what you think it actually does. I'll skip this one, although it's cool. So we kind of have these adversarial examples. And I will talk about this one. So this is really not about language at all. This is like RL tasks for Atari games. This is done with Shani Gamrian, who is pushing this forward. So you, I guess, know the game. You have this Atari game like Breakout, and you train some agent to play it. And it actually works pretty well. So here is, how do I make it larger? Okay. So here you can see it playing, and okay, it kind of learns to get the ball. You don't see the ball, but it's playing. Okay, and it can actually get to a very high score. So that's a success story. Okay, and it will finish the level soon, but I will stop it now. Let's go continue. But now we said, okay, so let's have this game and modify it slightly. Like we add this little piece of like block here, and this is not really a block. Like you don't hit it, just like go over it. It's just like this rectangle, like a visual change to the image. Or we can have like this change where you have lines on the image, and they don't. You kind of just change the background. You don't change the game, right? And then when you try to run the very same agent on this game, the modification, why doesn't? Try again. Okay. So yeah, it doesn't know what to do at all. Okay, it gets to like 2 points, and then it starts again. So it really fails on that. Even though we did not change the game, we only changed slightly the visuals. And this network really has no idea what to do, while a person would adapt perfectly to this, right? It's a very simple modification. So this is sort of a failure case of RL, but then we say, okay, so let's do fine-tuning, right? You kind of start with the weights of the initial network, and you then train it on or like fine-tune it on the new game until it will kind of transfer its knowledge and kind of learn to ignore these lines, right? It shouldn't be that hard. And there are various ways of doing fine-tuning, and when we do it, we see this story. Okay, so the red line is training from scratch, okay? And here you see the kind of training time and the score, so like higher is better. And you see that training from scratch is as effective, if not more effective, than all of these fine-tuning methods. So it's really hard to transfer knowledge from the game to the game with the lines or with the block. So this is with the lines, okay? And if you look at this single block there, you see that it's much worse. So you can get to pretty good accuracy if you just train from scratch. But if you try to adapt the first network, it really, really, really fails, right? It is much harder to adapt the network than to just forget everything and train from scratch, which for me seems that it's a very big failure case of RL because they're really overfitting like crazy to these things. And then okay, so it's as effective or much worse. And then we say, okay, so let's have our own approach of transfer learning. So not fine-tuning, but let's use GANs. Okay, so the idea would be to kind of think by some kind of analogy to the kind of previous game. So the agent will now collect images from the new game where it fails, and using unaligned GAN, we use unit GAN, we try to learn to translate from the new game to the old game, and then play as if it was playing the old game, okay? And this sort of works, which is nice, but let's see the video. Okay, so this is how the kind of game actually looks like. And over here, you can see what the gun imagines. So you can see that it learned to actually remove the green line, which is not surprising, but it's very easy to remove green lines. And as you can see, it keeps playing pretty well. And this is actually a nice way to do transfer, although as you can see, the gun is not perfect. Okay? But it did manage to kind of learn to play the game despite this kind of visual change. Okay, so this transfer by analogy, for me, is a nice story because it is much more sample efficient than fine-tuning. You need only, I don't know, 10K samples to kind of train this gun, while you need millions of samples to actually train the agent. And we believe it's more general than just like this kind of simple example with the lines. We can do it, I believe, with more complex tasks. So it's a transfer success story, but it is also, I think, a gun failure story. And why do I think that? Because, well, this is arguably the simplest image task possible. Okay, you need to remove a few green lines in a fixed position and keep everything else the same. Okay, it's a very, very simple task. And yet, we can see that it did not learn the right function, right? It translates from this to that, right? And it learned to translate from this to that, and so on, right? So it did not just learn to remove lines, it also did something weird with the blocks, okay? And basically, the gun did not learn the right translation, but a much, much more complex one, okay? And maybe it also happens with more complex guns, but now we can actually see it because we tried a very simple case, right? And I guess the lesson here is to try these more simple cases where you know what the actual answer is, so you can validate if your model is working or not. Right? Currently, guns are like very popular, but they are pretty much impossible to evaluate. Here we kind of give some way of evaluating them. You can see how well they will perform on the task of the actual game transfer, right? And we actually compare unit gun to cycle gun, and we see that like unit gun works much better than the cycle, which had much more problems like it kept moving the paddle and so on. Okay, so yeah, I would definitely look at simple cases that you know where the answer is. So this concludes my talk. Deep learning is great. You can do many amazing things with it, but it also had many failure modes and blind spots, and we should not be blind to these blind spots, okay? So don't be like swayed away by all the success stories. Try to look carefully at where things fail and consider the consequences of what it means to fail or what it means for the model. And one very good way of doing this, I think, is to look at the simpler cases where you know what the actual answer is and things that the network should definitely get right, and see that it actually fails on most of them. Thank you. I'll take questions now.